So first chapter and second term is mechanical property of solids. Suppose you have spring having natural length L to this point. Now, if you stretch it or compress it, to this or to this point, a force will develop into it, which will tend to bring back or bring this particular spring back to its original shape. So in this part, if you compress it along this direction, or if you stretch it along this direction, a force will develop into it opposite to its compression or expansion. So in this, it will be in this direction, and in this, it will be along this direction. This force will have tendency to regain its original shape or configuration. This force is termed as restoring force. And the force which changes shape while compression or expansion is termed as deforming force. So initially, a deforming force was acting on this spring to compress it or stretch it. Due to its compression or expansion, a force get developed into it, which will tend to bring back to its original configuration, that is called restoring force. Is it clear till this part?
Yes, sir.
Now, due to this restoring force, body having tendency to regain its original shape, so we can define a term that is called elasticity. So whenever a deforming force acts on a body to deform its shape, if the property of a body to regain its original shape on removal of deforming force, then this tendency or property is defined as elasticity. Similarly, we may define for any solid, let's say, if particles in a solid are arranged at the vertex of a cube, and bonding in between them behaves as spring-like structure, due to which it having tendency of regaining its original shape. So if you apply any deforming force on this cube to extend or deform this solid to this point, a force will develop on it to bring back to its original shape. This tendency of solid to regain its original shape on removal of deforming force is termed as elasticity. So elasticity is the tendency of a body to regain its original shape on removal of deforming force is termed as elasticity. Similarly, we may define the opposite term of this elasticity is plasticity. If a body having inability to regain its original shape on removal of deforming force, then it is termed as plasticity. The inability of a body so that they can't regain their original state or shape on removal of deforming force is termed as plasticity. Is it clear to everyone?
Yes, sir.
Yes, sir.
In general, there is no any object which is perfectly elastic or perfectly plastic. So the property of body lies in between elasticity and plasticity. So you'll say behavior of solid lies in between elastic and plastic nature. Just write it down to this part. You all have written?
1 minute, sir.
Yusuf, any doubt?
No, sir.
Done, sir.
Yusuf, you have written?
Yes, sir. 1 minute. Sir, writing plasticity.
Okay. Rishan,
Done, sir.
now for this deformation, we may define some of term. First is stress. Suppose there is a solid which is hanged from any support, and if a force applied on it along this direction to deform its shape, so it will be deforming force, due to which this rod gets slightly extended to this point. So actual length of rod is L from this point to this point, and deformation is from this point to this point. Area of cross section of rod is A. So first, stress is the amount of deforming force acting or applied on a particular solid per unit area is termed as stress. So stress is the amount of deforming force applied on a body per unit area. So stress equals to deforming force divided by area of cross section. Unit of force is Newton and unit of area is meter square. So its SI unit is Newton per meter square. Is it clear? Yusuf?
Yes, sir.
Now, due to this particular stress, there is deformation in this particular rod by dl. If you relate this particular deformation with respect to its original, we may define another term, that is strain. So strain basically defines you amount of deformation produced in this particular solid with respect to its original shape. So it is nothing but ratio. The ratio of deformed shape to the original configuration. So strain is equals to deformed shape of body divided by its original shape. In this solid, deformation is delta L and original shape of the body is L. So it will be delta L divided by L. As in numerator and denominator, we have same term or quantity having same unit. So you'll say it will be unitless or dimensionless quantity. Abhinav, is it clear?
Yes, sir.
Okay, just write it down. All have written.
Yes, sir.
Now there is relation between the stress and strain developed, which is defined by Hooke's law. It states if temperature is fixed or keep it as constant and within elastic limit, I will define you later what do you mean by elastic limits. The more you apply stress to a particular body, the more strain will develop into it. It means stress and strain correspondingly proportional to each other. So you'll say at constant temperature, and within elastic limit, the strain developed or produced in a body is directly proportional to the applied stress. So you'll say stress and strain should be directly proportional to each other. Now, if you replace this proportionality sign by any constant term, so it will be stress equals to E times strain, where E is called modulus of elasticity. And if you draw a graph between stress and strain, since stress is directly proportional to strain, so it will be a straight line like this. So if you simplify it or rearrange this equation, you'll get E equals to stress divided by strain, which is equals to, related to this particular graph, as slope of stress strain curve. So if there is angle theta, so tan theta of this particular curve will define you the value of modulus of elasticity. Is it clear? Abhinav?
Yes, sir. Clear, sir.
Okay. Now, what are the factors on which this modulus of elasticity would depend? So you'll say, first, it will depend upon temperature, and the second, the nature of material. It will be independent of dimension of body. So this modulus of elasticity simply defines you the elastic behavior of a particular solid. It defines the elastic behavior of a solid. It depends upon temperature and nature of material, and it will be independent of dimension of body. Yusuf, any doubt?
No, sir.
Nida, is it clear till this part?
Yes, sir.
Okay.
Done, sir.
1 minute, sir. Last. That's it.
Okay. Now, depending upon these three terms, we may define its type. First is, suppose you have a solid. Support. If deformation is produced along this direction to extend this particular solid, it will be termed as longitudinal. And if deformation or deforming force is applied on this particular solid to compress it, it will be termed as compressile. Now, due to which this solid may slightly deformed along this to this part. This will be actual length of solid, and this will be amount of deformation produced, that is delta L. Similarly, in this part, total length of solid is L, and deformation will be till this part, delta L. So first is longitudinal or compressive stress. So it will be deforming force to extend it or to compress it. So force per unit area. Correspondingly, amount of deformation produced will be longitudinal strain equals to delta L divided by L. Now, if you divide these two terms to get the value of modulus of elasticity, in this longitudinal term, it will be termed as, or it is called, modulus of elasticity or Young's modulus. So it is equals to longitudinal stress divided by longitudinal strain. Young's modulus is denoted by Y. Longitudinal stress is force divided by area. Longitudinal strain is delta L divided by L. So on simplifying it, you will get F into L divided by A into delta L. So this will be your formula for Young's modulus. Now, in this part, I'm defining along its length. So Young's modulus will define you elasticity in length of a body. Is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
Yusuf, done?
Sir, writing the formula.
Okay.
Done, sir.
Okay, I'm giving you a question related to this. A force of 20 kilonewton is applied on 2-meter long wire having cross section 4 mm squared. Find stress, strain if Young's modulus is 2 into 10 raised power 11 Newton per meter squared. And third, elongation produced. Just use the above formula and try to find these terms. You have force is equals to 20 kilonewton. So you have to write all of the quantity in terms of SI unit. So in terms of SI unit, it will be 20 into 10 raised power 3 Newton. Second is, it is 2-meter long. So length will be 2 meter. And area of cross section is 4 mm square. So to convert it in terms of meter square, just multiply it by 10 raised power minus 6. And the last, you have the value of Young's modulus, which is 10 raised power 11 Newton per meter square. Just use these values to find the value of stress, strain, and elongation. Try to solve. Stress equals to deforming force by area. Just put the value of these two terms. For strain,
Sir, is my answer correct?
just 1 minute. Check your calculation.
Okay, sir.
Strain is equals to delta L by L, or you may use Young's modulus is equals to stress divided by strain. Just use these three different formula to find all of them. Nida, just check your calculation. We have force is 20 into 10 to the power 3. Area is 4 into 10 to the power minus 6. So this 4 cancel out this 20 in 5 times. Good, Nida. And this we have 10 to the power minus 6 in denominator. Good, Yusuf. So on moving to numerator, it will become plus 6. So 5 into 10 to the power 3 plus 6. It will be 5 into 10 to the power plus 9 Newton per meter square. Now for strain, since in this question we don't have delta L, so we don't use this formula. So just use this term. So strain will equals to stress divided by Young's modulus. You have calculated the value of stress, and there is already given in the question the value of Young's modulus. Put these values and try to find the value of strain. Good, Nida. Just use the second formula to find the value of delta L or elongation produced. So strain is equals to a stress divided by Young's modulus. Stress we have calculated as 5 into 10 to the power 9. Young's modulus is 2 into 10 to the power 11. So 5 divided by 2, it will be 2.5 into, if you move this denominator to numerator, it will become 10 to the power minus 11. So 9 minus 11, it will be minus 2, like this. Yusuf, just check your calculation. Okay, so for third part, strain is equals to delta L divided by L. So delta L will be L times strain. Length of fire is 2 and strain developed is 2.5 into 10 to the power minus 2. So 2 into 2.5, it will be 5 into 10 to the power minus 2. In terms of meter, so if in terms of centimeter, it will be just 5 centimeter. Abhinav, is it clear?
Clear, sir.
Good, Nida. Yusuf, is it clear?
Yes, sir, it's clear.
Okay. You all have written?
Yes, sir.
Now the second type is, suppose you have a cylindrical blob whose base is kept fixed. Now, if you apply tangential force to it, I have assumed this base to be fixed. Then, if we apply tangential force to it, it will slightly bend. Like this, if a tangential force is applied on it. Initially, it was at this point. Now due to deformation, it is slightly displaced to this. Having displaced portion x, length of this particular cylindrical block is L, and this will be theta. So this is termed as tangential or shear. So first is shear stress equals to tangential force acting on solid by area of cross section. Correspondingly, amount of strain developed will be shear strain, and it will be theta, which is equals to x by L. And if you divide these two terms to get modulus of elasticity, in this term, it will define shear modulus. So shear modulus equals to shear stress divided by shear strain. Shear modulus is denoted by capital G. Shear stress is tangential force divided by area, and shear strain is theta. You may simplify it F by A, X by L. So this will be a formula for calculation of shear modulus. In this part, it is deforming along its shape. So this shear modulus will define you elasticity of body in shape. Is it clear?
Yes, sir. Clear, sir.
Riba, any doubt?
No, sir.
Okay. Rishan, is it clear till this part?
Done, sir.
Yusuf?
Done, sir.
Okay. Suppose a cube of side 10 centimeter, whose one face is kept fixed. Now, a force of 20 kilonewton is applied tangentially to its upper face. Find shear stress. Suppose in this part we have a cubicle or a cube like this. And a force is applied tangentially along this direction, keeping base to be fixed, due to which it gets slightly deformed. Let's say to this point. So you have to find shear stress produced in this. Since you have side of cube as 10 centimeter, so area will be length into breadth, 10 divided by 100 into 10 divided by 100. So it will be 10 to the power minus 2 meters squared. Force is given, convert it in terms of SI unit, and just divide these two terms to get the value of shear stress. Try to solve. Good, Nida. Good, Yusuf. Abhinav, send me your answer. Riba, Umar, we have force is equals to 20 kilonewton. So it will be 10 to the power 3 Newton. Shear stress is basically tangential force applied per unit area. Tangential force is 20 into 10 to the power 3 divided by area 10 to the power minus 2. So if we move this term to numerator, it will become 10 to the power plus 5. And if you move this 0, you'll write it as 2 into 10 to the power 6 Newton per meter square. Is it clear to all of you?
Yes, sir, clear.
Abhinav, any doubt?